In this lesson, we'll show some applications of rational equations. We'll go over several types of word problems. The first type will be proportion problems. As we know, a proportion is a comparison of two ratios. To make sure that a proportion is written correctly, we need to remember to keep the same type of data at the same level. So for example, if we have two categories, we keep them at different levels, and the same type of data, for example, data before certain change, should be kept in one and the same fraction, and data after certain change in the other fraction. So let's see an application problem that can be solved by using proportions. To estimate the number of wild horses in California, a forest ranger catches 616 wild horses, tags them, and releases them. Later, 244 horses are caught, and it is found that 49 of them are tagged. Assuming that the horses mixed freely when they are released, estimate how many wild horses are in California. So what do we have here? We have 616 wild horses that were tagged and then released. They mixed freely with other wild horses, and then 244 horses are caught. Those 244 horses contained 49 that were tagged. What are we asked for? Estimate how many wild horses are in California. So all horses in California, that's what we are after. Okay, so let's introduce a variable. Let x be the number of wild horses in California. So this part is x. Let's represent the whole population and the tagged sample by two concentric circles like this. Okay, so we have 616 horses that were originally caught out of x wild horses. Now, the horses that were caught second time, 244, that will be our sample. Let's represent this 244 horses by a sector of our circle. 244 is, let's say, this sector of the whole circle that represents all horses in California. It happens that among those 244, 49, the white portion of the sample sector, were tagged. So let's try to put together a proportion. In a proportion, we have to be really clear what kind of categories we use and whether we refer to the total population or to the sample. So our categories will be horses that were tagged in the numerator and all wild horses in the denominator. So we have x of all wild horses in California. That's the unknown. Out of those x horses, how many were tagged? 616. So we can place this number here. 616 corresponds to x in the same way as in the sample we compare the tagged ones to all horses, 49 out of 244. As soon as we write this proportion correctly, 90% of the problem is done. We know how to solve it. Remember, to solve a proportion for an unknown, we multiply numbers that we see across and divide by the third number that was not used. Okay, we can use calculator for this part. It turns out to be 3067 when we round it to the nearest horse. So we can give the final answer. There are approximately 3067 wild horses in California. Why the question calls for an estimation rather than exact answer? What do you think? Well, we assume that the ratio of tagged to all horses is exactly the same for the sample and for the population. However, in reality, these two ratios are equal only approximately. Why? Well, for example, picking different samples will most likely produce different ratios. So the actual number of wild horses in California could be a little bit off. We have no guarantee that it will be 3067. Nevertheless, we could say with a big probability that approximately 3000 wild horses lives in California. Let's see another type of word problems. This bunch will refer to the famous theorem in geometry called Thales theorem. This theorem is about properties of similar triangles. Here we have a diagram of two similar triangles ABC and AB prime C prime. The theorem states that two triangles are similar if and only if their corresponding sides are proportional. That means that if the two triangles are similar, similarity can be marked by a wave like that, then we know that the ratios of corresponding sides of these two triangles are the same. Particularly, AB over AB prime is the same as AC over AC prime, and it's the same as BC over B prime C prime. Also, the other way around, if the ratios of the corresponding sides are the same, then the triangles are similar. Very powerful theorem. Let's see an application of it. Using the information given in the diagram below, find the value of the height h in meters at which the tennis ball must be hit so that it will just pass over the net and land 6 meters away from the base of the net. So, we have a diagram. We don't need any let statement because all information are already here. We are looking for the height h such that this tennis ball will pass just over the net that is of 0.9 meters high and land 6 meters after the net. From this diagram, we also know that the horizontal distance of the ball from the net is 12 meters. So, since the net and the height of the ball are both vertical, these two triangles are similar, and we can set up a proportion. The height to the base of the big triangle is the same as the height to the base of the small triangle. So let's set it up. H over this whole base is 12 plus 6, so it's 18. Is the same as 0.9 over the base, which is 6. And then we solve it. So keep the variable h and then multiply across 0.9 times 18 and divide by the remaining number, which is 6. We can reduce 6 with 18, leaving 3 in the top, and we end up with 3 times 0.9, which is 2.7. Everything was in meters, so our answer is in meters as well. And we're ready to give the final answer. The height is 2.7 meters. Yeah, that's all. Let's see another type of problems, motion problems. Probably our favorite ones, right? When solving motion problems, I would suggest to stick with a table like this. Rate times time equals distance. Those are our columns. And then possibly first movement, second movement, and occasionally total. This total line, sometimes it's needed, sometimes it's not, depending on the problem. Also, in motion problems, we can add times or distances, but we usually don't add rates. So keep this in mind. We're not adding this column. We may add or subtract this column or that column. Let's see a particular example. The speed of a car is 5 miles per hour faster than the speed of a bus. The car travels 220 miles in the same time it takes the bus to travel 200 miles. Find the speed of the car and the speed of the bus. So we have two moving objects, the car and the bus, and we have some information that we can organize in a table like this. Let's see the question again. Find the speed of the car and the speed of the bus. So we need to find two things, right? But if we want to use just one variable, we need to make a decision. Introduce a variable for the speed of the car or a variable for the speed of the bus. What's better? Since from the first sentence, we know that the speed of the car is 5 miles per hour faster than the speed of the bus. Therefore, it's easier to set up a variable for the slower vehicle, so we can use addition for the faster one. Okay, let R be the speed of the bus then. We have two vehicles, car and a bus. Rate times time equals distance. Let's try to fill in those empty boxes. We already introduced R for the speed of the bus, so that will be here. Now, what would be the expression representing the speed of the car? Well, car is 5 miles per hour faster than a bus, so 5 faster than R. Therefore, it's R plus 5. That's the rate of the car. What else do we know? The car travels 220 miles. That's about distance. and it's about car. So we put this information in the row of car under the distance, 220 miles. In the same time, it takes the bus to travel 200 miles. Okay, so that's the distance for the bus, 200 in a bus row. What else is important? They gave us information that both vehicles traveled in the same time. We don't have a value for this time. However, we know that whatever the expression comes for the time of the car will be equal to the expression that will come for the time of the bus. Okay, what is this expression? Well, let's follow the formula that is written in the top. To find out time from this formula, what we need to do is take the distance and divide by rate. So let's follow this recipe. Distance over rate, 220 over r plus 5. In the bottom, again, distance over rate, it's 200 over r. And that's how we develop our equation. So we can write it down on the side, 220 over r plus 5. Time of the car equals time of the bus, which is 200 over r. Again, we end up with a proportion. To solve this proportion, we can just cross multiply. But before we do that, we can make our numbers a little bit simpler. We could, for example, divide by 10 both sides, and even more, divide by 2 again. So the 20 divided by 2 is 10, 22 by 2 is 11. This will make our numbers smaller and easier to calculate. So let's cross multiply. 11 times r equals 10 times r plus 5. So we have 10 times r plus 10 times 5, which is 50. And then if we subtract 10r from 11r, we end up with r on the left, and it's 50. Great, so we have the speed of the bus, 50 miles per hour. Now, since the question calls for both the bus and the car, speed of the car would be r plus 5, which is 50 plus 5, so it's 55 miles per hour. And we are ready to give the answer. The speed of the bus is 50 miles per hour, and the speed of the car is 55 miles per hour. Another motion example. A plane travels 100 miles against the wind in the same time that it takes to travel 120 miles with the wind. If the speed of the wind is 20 miles per hour, find the rate of the plane in still air. So this time we have one moving object, just one plane. However, in the first situation the plane goes against the wind, and later on it goes with the wind. That will be something to watch. What does the question ask for? Find the rate of the plane in still air. So the rate of the plane, that's our unknown. Let's introduce it. Let r be the rate of the plane in still air. And then we set up a table, rate times time equals distance, with two possible situations, with the wind and against the wind. Okay, let's read it again and try to fill up those boxes. A plane travels 100 miles against the wind. So this 100 miles really represents distance. So 100 goes where the distance is, and we are in against the wind situation. So here, 100. In the same time, okay, the time is going to be the same, so we're going to develop equation by comparing these two time boxes, right? It takes to travel 120 miles with the wind. Again, distance, because it's about miles, 120 in the situation when the plane goes with the wind. If the speed of the wind is 20 miles per hour, find the rate of the plane in still air. Okay, what is the speed of the plane that goes with the wind? The plane is flying with its own speed, which is r, and on the top of it, the wind is adding to its speed. The speed of the wind is 20 miles per hour, so we add 20 to it for the overall speed, right? However, when the plane returns the other way around, even though it goes with the same speed r, and the wind blows in the same direction, that's our 20 miles per hour, the overall speed of the plane will be diminished. It will be just this much, right? Because the red minus the green, it's actually equals to the blue. So the formula for the overall speed is r minus 20, isn't it? Okay, the rate of the plane with the wind is r plus 20, and against the wind is r minus 20. And now we have everything what we need. To find out the expression for the time, we use the formula distance over rate, right? Let's write it again. Time is distance over rate. So this column divided by that column, 120 over r plus 20 equals to 100 over r minus 20. Okay, so that's our equation. Let's write it down and solve it. 120 over r plus 20 equals 100 over r minus 20. Again, we could cross multiply as it is, but it will be a bit easier if we simplify whatever we can. For example, we could divide both fractions by 10. We could even divide by another 2. So 12 by 2 will be 6, and here 10 by 2 would be 5. Okay, let's cross multiply. 5 times r plus 20 gives us 5r plus 5 times 20, which is 100, equals 6 times r minus 20, so 6r minus 6 times 20, 120. Let's isolate r's. Since there's more r's on the right hand side, let's bring the 5r to the right. That becomes 6r minus 5r gives us just a single r. And then we bring 120 to the left. It becomes positive 120 plus 100. It is 220. That's our r, which is the rate of the plane in still air. So that's exactly what we're supposed to find, right? Let's give the final answer. The rate of the plane in still air is 220 miles per hour. That must be a very small plane. Another type of problems, work problems. They are quite similar to motion problems. However, instead of just regular rate times time equals distance, now instead of distance, we'll have amount of job done. So rate of performing the job times time of performing this job equals the amount of job done. Usually this amount of job done is just 1, but not always. Let's see an example. David can paint a house in 12 hours. Bill can paint the same house in 9 hours. How long will it take them to paint the house together? Okay, so let's set up a table. Rate times time equals job. And in the table, we'll arrange information about David, Bill, and when they work together. The job that we're talking about is just painting the whole house. So it's the same one job for David, Bill, or if they work together. Since the question calls for how long will it take them to paint the house together, our variable that we are after is in this box. It's time for together. Let's call it t. What else do we know? David needs 12 hours, so 12 goes here. Bill needs 9 hours, so 9 goes there. Okay, so we have all information that were given in the question. What do we know about rate of performing the job? Well, according to this formula, rate is the same as the job done, which is 1 in our case, 1 over time, 1 over t. Also notice that if two people work together, the rate of performing the job should add. That's the difference between work problems and motion problems. In work problems, we usually add rates. Remember, in motion problems, we usually do not add rates. But in work problems, we usually add rates. However, we do not add times. Because if David needs 12 hours, and Bill will come and help him, together they should need less than 12 hours. Similarly, if Bill needs 9 hours and David will come to help him, they should complete the job in less than 9 hours. So keep in mind that the time together in work type of problems is always shorter than any of the individual times. However, rates add. Okay, so let's fill up the rate column. That will be 1 over 12, 1 over 9, and 1 over t, 1 over the time that we don't know. The equation comes from comparing the rates, adding these two rates, and that's supposed to be equal to the overall rate 1 over t. So let's write it down. 1 over 12 plus 1 over 9 should be equal 1 over t. And as you see, we have a rational equation to solve. How can we solve it? By multiplying by LCD. What's the LCD for 12 and 9? 36 should work, right? And also t, so 36t. Let's multiply by it. 36t divided by 12 is 3t, plus 36t divided by 9 is 4t. And finally, 36t divided by t is 36. That's how we clear our fractions, and we end up with an easy linear equation to solve. So we have 7t equals 36. Therefore, t by itself is 36 divided by 7, which is really 5. The t was in hours, so it's 5 hours and 1/7. That's an exact answer, but it's not very convenient in this situation, isn't it? Because in real life, we would like to know how many hours, how many minutes, rather than 5 and 1/7 of an hour, right? So we know it's 5 hours for sure, and a little bit. This little bit, 1/7, using calculator, that's the same as approximately 8.6 minutes. That's pretty exact anyway. 5 hours and a little bit more than 8 minutes. Let's round it to 5 hours 9 minutes. So we can give the final answer. If working together, it will take them approximately 5 hours and let's say 9 minutes to paint the house. Okay. And the last work problem example. A tank can be filled in 9 hours and drained in 11 hours. How long will it take to fill the tank if the drain is left open? Okay. Again, let's fill up the table rate times time equals 1 job to do. This time we have filling in situation and draining out. So that's kind of different, right? This draining out is like undoing the job that was done by filling. How long will it take to fill the tank if the drain is left open? So we have one row that refers to filling in, the other row that refers to draining out, that means undoing the job, and last row, what will happen together. What do we know? Filling in takes 9 hours. 9 goes here. Draining out takes 11 hours. 11 goes there. Together, well, we don't know. That's exactly the question. How long? So let's t represents the time needed to fill the tank if the drain is left open. And then we use the formula that is in the top. Rate is 1 divided by time. So it's 1/9 here, 1/11 over there, and 1/t in the last box. Okay, but the difference between this question and the previous one is that we're not adding these rates because they don't work together, they work against each other. Since the draining is undoing the job, we're going to subtract it. So the rate of filling in, 1/9, minus the rate of draining out, 1/11, equals the overall rate when the drain is left open, 1/t. And again, let's multiply by least common denominator, which is 99t. That gives us 99t divided by 9 is 11t. 99t divided by 11 is 9t. And 99t divided by t is 99. Okay, 11t minus 9t, it's 2t equals 99. Therefore, the single t is 99 divided by 2, which is 49.5 hours. And we are ready to give the final answer. It will take 49.5 hours to fill the tank if the drain is left open. And now it's your turn. Take some problems and practice.